Hello, my name is Peter Anzadeo, and this is my presentation on the first lab for Physics 2211 on constant velocity. So what exactly is the main purpose of this lab? Well, we are investigating into the concept of constant velocity by essentially looking over a time period, an object, which I chose as an expo marker that appears to be moving with constant velocity, and comparing the observations from this video to a computational model which I've created based on the conditions of the real-life model, real-life motion, I should say, using GlowScript. And ultimately, we are looking to extract some sort of difference between the observations that we see in the actual video versus the computational model in order to help us better understand the concept of constant velocity. And so the physical principle that we're looking at here is that when an object is in motion with a total net force of 0, essentially it must be moving at constant velocity. And the two models we are using for this lab are the video, which we recorded and uploaded to Tracker, and then the computational model, which we created with the use of GlowScript. And essentially, in the end, we see that the distance the object / expo marker travels as predicted by the computational model will be greater than the distance it travels in real life. And so the main physics ideas that we have at work here start from Newton's second law, which is essentially the momentum principle, where you see that the net forces on an object are essentially equal to the change in momentum over the change in time in the scope of the motion when the time interval is small enough. And so we rearrange that by multiplying delta t on each side. We get delta p is equal to the net force times delta t, which is essentially the momentum update formula. And then based on the principle that momentum equals the mass of the object times its velocity, we can see that velocity equals momentum divided by the object's mass. And so we divide everything in the momentum update formula by the mass, m, to get ourselves the velocity update formula, Vf equals Vi plus F net over m times delta t. And essentially what we see here is that when the net force on the object is 0, the whole second half of this velocity update formula after the addition symbol here just goes away, and we're left with the initial velocity equaling the final velocity. So yeah, we see that when net force is 0, velocity is constant. And this is an essential concept for this lab, and that we will use in GlowScript, as well as the position update formula, which I will show here. In line 60, we have the velocity update formula, and we see that since F net, since we set that equal to 0 right here in line 56, this whole part of the equation will go away, and initial velocity of the ball will equal the final velocity of the ball for the loop that we're doing. And then here's the position update formula, which I talked about, which is important to getting the data and the graph back from this computational model. This computational model is based on the tracker data that we collected. We can see that the origin / starting point of the object, the expo markers here. I don't have it shown, but here's the y-axis. Oops, sorry about that. Here is the y-axis essentially, and the x-axis is essentially along the motion of the expo marker. And so we get the initial conditions used in the computational model from the data we collected here by doing the distance the expo marker traveled over 1.033 second interval, which gives us this initial velocity, which is the constant velocity, 1.335. And in the experiment itself, the system is the object in motion, which for the video is the expo marker, and for the computational model is the ball, and the surroundings are everything else, for example, the table. And so what exactly are the conclusions? Well, we can conclude that the position of the object as predicted by the computational model grew farther from the actually observed position of the expo marker in the video as time increased. And why was there a difference? Well, we can likely conclude that there is a difference because the computational model that we coded does not take into effect the forces of friction or air drag, because we never coded anything for them, and those are actual forces in real life that slowed down the object And as you can see, at time t equals 0.4 seconds here, the experimental position, the actual position we see from the video, is not as far, or I guess I should say is not as great as the position which is predicted by the computational model. And so what if the axes were flipped, the x-axis, essentially the same concept. And so that's it. Thank you for watching.